Oh, good evening, everyone. I'm Gary Hatfield, and I am here with the Minnesota Center for Financial and Actual Mathematics. This is our weekly Friday seminar. This is actually our last Friday seminar for the fall of 2020. Although we are working on our set of speakers for the spring, we've already got a couple of people lined up that I'm actually pretty excited about. So stay tuned because I think there's going to be some really excellent speakers coming up this spring as well. Um, it's my pleasure tonight to introduce to you Professor David Matteson, who is affiliated with the School of Statistics and Data Science at Cornell University. He's a member of the ILR School, Computing Information Services, the Center for Applied Mathematics, the Field of Operations Research, and the Program in Financial Engineering. So I think apparently he does everything. Um, David teaches statistics, data science, and financial engineering courses. Um, he's actually an alum of the University of Minnesota, having received a bachelor's degree in finance, mathematics, and statistics. And then he went on to earn a PhD in statistics at the University of Chicago. I'm not going to list everything here, but I will mention he's a co-author of a book called Statistics and Data Analysis for Financial Engineering, which, by the way, I've looked at as a potential something that we might use, and I think it's actually a pretty nice book. So well done, David. But I will say that David's got numerous NSF grants, numerous involvement with the National Science Foundation, very active in the American Statistical Association, and as a associate editor of a number of statistical journals. So uh, with that in mind, I'm just going to turn it over to David and let him take the hour. And I think, given the size of the group here, I think people raise your hand and ask questions if something comes up.
Thank you so much, Gary, and thank you very much for the invitation. It's really a pleasure to speak to this group. When I was a student in high school, actually, I was in Roseville, a suburb of St. Paul, and I took my last 2 years of high school at the university, and I got very far ahead in my math coursework in particular. That's why I was able to do a triple major. I did want to mention that I started in the business school actually, and I liked finance, but given all the math courses I had taken, I was finding it a little unsatisfactory in terms of sophistication mathematically. And I found these financial math courses that were offered in the math department. And I was also trying to have a go at taking real analysis course at the time too. I think he's still at the school now, Carlos Tomaski. He was my instructor, and we read maybe like the second edition of Hull's book, and I took 2 semesters of that class. And this was before this new Center of Financial Math and Actuarial Math was even founded. I think it was kind of a precursor to that. And I just remember just being absolutely fascinated with the application of math in that way and in that context, and thinking about risk and uncertainty and continuous time modeling. And that really inspired where I ended up in terms of PhD work. I ultimately decided a statistics department, but I went somewhere that had a big emphasis on financial math as well. I did pivot. Once I got to Chicago, I found that time series was maybe my true passion, financial time series in particular. And I've diversified a little, but my time at Minnesota was really special and dear to me. So with that, I'll go ahead and share screen. Today, I'm going to talk about something we call dynamic shrinkage processes. I'm going to try to make this full screen. Let me know if, can you still see the screen slides, Gary?
I can still see the slides, but it's not full screen. It's just,
okay.
It looks like what's on your display.
Let me just share the whole desktop. This is the dangerous thing they tell us not to do when we're teaching online. But all right, desktop, and Is that full screen now?
Yes.
Good deal. All right. I'm going to talk about something called dynamic shrinkage process, and if time, I'll mention a couple of important extensions of this. So this is joint work with a former PhD student of mine, Dan, who's now at Rice University, and my longtime collaborator and mentor, David Rupert, professor at Cornell. So this work recently appeared in JRSSP. The preprint that's not behind a paywall is available online as well. So just as a little motivation, I want to talk about time-varying parameter models. But first, let's start with maybe a familiar model from empirical finance. So let's consider a simple scalar response, y, and let's consider a set of p predictors. Okay. And we'll run I say this is a static regression in that although the different variables are indexed by time, the slope coefficients beta are not. So these coefficients are a fixed functional relationship between the conditional expectation of y given x. And the most common example would be something like the capital asset pricing model in finance, or extensions of the FAM French flavor. So in particular, y might represent asset returns or standardized asset returns. So sometimes we refer to that as excess returns in excess of the risk-free rate. And X would typically represent what are called factors, financial factors that explain the primary co-movements in asset prices. So when we want to explain the variation in returns for a portfolio Y or a particular asset Y, we regress on fundamental factors. So these are observable factors. They might be constructed, but they're available to us. They're sometimes called fundamental factors. So they're different than statistical factors. So these are given variables that maybe someone has provided. They're not latent. So in particular, what are the types of things that might go into X? So here's an example of 6 different components that X might include. So I mentioned the capital asset pricing model. So one component of X might be the excess return of the market itself. So this goes back a long time. But with that single predictor is what we might refer to as the capital asset pricing model. How you actually define what the market is and what the market return is, it's continually up to debate, but you might use something like the S&P 500 returns as a proxy, at least for illustration. Other fundamental factors that have been quite popular include those from FAM and French 3-factor model. So a factor for size. And this is the relative return of small firms versus big firms with respect to market capitalization. There's different ways to split this up. Value, fundamental factor for value, comparing the overall net asset values, book to market ratios of different firms. More recently, there's new factors that have shown to have high explanatory power. When I was a student at the University of Chicago, I took a PhD courses with Eugene Fama in the business school. He assured us that there was only 3 important factors, but after I graduated, lo and behold, there was 4th and 5th ones that were published. So profitability, robust minus weak, investment, conservative minus aggressive, and momentum factors. So we can put all these regressors into the model, and maybe now we have an intercept in 6 components. Again, we would think about standardizing a response to account for the risk-free rate. And we can consider portfolios that are constructed off of different sectors, just for illustration. So in today's talk, I'll think about the manufacturing portfolio constructed from the manufacturing sector, and then just as a contrast, portfolio constructed in the healthcare sector. This data is slightly old now, so it'd be very interesting to update this through our pandemic period in particular. I'm going to look at weekly data. There's no particular reason other than, I wanted quite a bit of data, but daily was maybe a little too dense for the illustrative purposes. So I've got a couple decades worth of weekly returns. So my time series is going to be a length around 1,000. Okay. So I fit one of these models. In this case, it was fit on the manufacturing industry first. And let's look at a couple things. So these are time series plots of something that I'll try to describe. So each panel is corresponds to one of the regression coefficients. So it's the beta associated with a particular regression. So there's a beta associated with the intercept term, a beta associated with the market return, small minus big, high minus low, etc. The black line is just the zero line for reference. Okay, so if a fundamental factor is important, it should have an estimate that's far from zero, given some measure of uncertainty. If it's relatively unimportant or of little practical significance, its estimate should be near zero. The dashed green lines are the static OLS estimates. Okay, so that's from the model that I introduced on the earlier slides. So they're not time varying, they just stay fixed. So let's just look at those one as we go across. It seems like the intercept's a little bit below zero. There's a question of whether or not it's significantly different than zero. You know, arbitrage theory says that it should not be different from zero if we've accounted for all of the variation through factors. How about the market return? Well, its beta is about 1 in this model. When we interpret the beta, it's of course conditional on all the other variables that are entered into the model. But this seems quite far from zero. Okay, so the market return has quite a bit of explanatory power. Again, we should validate that given how uncertain we are about this parameter. Other ones seem more or less close to zero. All right, how about these blue curves? What are these? Imagine fitting our static model, but only using half of years worth of data. Okay, so in this illustration, I had 20 years worth of data. Okay, but now let's just take 6 months. And let's 6 months of weekly data, let's estimate our static model. For this, so for the first 6 months of this 20-year period, I get a slope coefficient for the intercept. I get a coefficient for the risk-free market rate. And now I roll that window forward. Okay, I just move, I add a week of the more recent time and I remove a week from the end. So the width of the window always stays the same, and I just keep fitting my static regression. And what do we see from doing that? Well, we see that the coefficients are actually evolving over time. Okay. Of course, there's sampling variation. So we have a relatively small sample when we're only taking 6 months of weekly returns. So variation itself is expected, but we start to look for patterns. So in particular, in about the middle of the time series, there's a big jump in the market. At the same time, there's a sign change in small minus big. It went from positive to negative. High minus low wasn't quite as sudden, but it did also have that sign reversal. How about this momentum factor? Well, all of a sudden in 2007, 2008, momentum was very significant positive beta, but it wasn't sustained. Okay, so over this short window, this was a very important predictor retrospectively. Overall though, because it was negative before and after, it washed out. An ordinary least squares model, the green line, missed this completely. Okay. So the motivation of time varying parameter models is a formalization of this kind of rolling static approach. Okay. So there's nothing intrinsically wrong about doing the rolling window approach, but we might suppose a model for the evolution of these coefficients themselves. Why should we support using time varying models at all? Well, when we think about all the variables we account for our regression and the fact that there's an infinite number of influences on the economy, we might wish to be a little bit more flexible. So think about turnovers in administrations at the Federal Reserve Board in particular, changes in regulatory conditions, monetary policy, different institutional frameworks, and then different bilateral and international relations in terms of trade networks. These can have a big impact on the way financial markets allocate variability and allocate risk. So having a little bit more flexibility, allowing our parameters to change over time, maybe with a restriction that they change somewhat smoothly, can have a lot of advantages. So what's the change? How do we make this a dynamic regression? Okay, well, it has two parts. So on the top part, it's the same equation as before, except for now we've added a t to our betas. We're going to allow the betas to evolve over time. Okay. How should they evolve? Well, the simplest model of evolution might be just a random walk style model. Okay. So the next value of the coefficient should be centered at the current value plus some kind of noise. So if we're willing to adopt this style of model, then a real question is, what should the distribution or penalty be for this innovation omega? Okay. How much evolution should there be over time? Traditional white random walk model says that this is an IID process, or at least a white noise process. But maybe we want this to have kind of a flexible variability. There might be times when we want little evolution in the process, and omega should be very close to zero. And other times when we'd like omega to be large in magnitude, but with no particular direction. So we'd like added volatility for omega. In either case, the point is to push the beta path forward in some stochastic way. So here's a simpler example where we just regress on an intercept-only model. Okay, so I have a response y, a scalar coefficient beta. So this is the case where we have just the covariate itself is just an intercept. It's just the one, vector of ones in the vector case. Okay, so there's and this is also just commonly called a signal plus noise model. So I've got a signal I want to track, beta. It's the mean of the y's locally, and then there's some noise. In trend filtering, what we're interested in is under the assumption that there's some smoothness in beta, also co-studying the increments in beta. So delta would be the difference operator. When I have delta raised to say the kth or second power in this case, I might consider second differences in omega and request that those be small in general. So small second differences means not too much curvature in the path of beta, the coefficient that's evolving, and that induces a relative amount of smoothness in the path. This is not universally desirable, but it's a simple place to start. Certainly if you're running your rolling static regression, that's inducing smoothness because one point is entering, one time point's exiting, and there's a lot of overlap from neighboring time periods. Just a reminder, if we take second differences of this process beta at time t+1, that's looking at the increment in the first differences. And of course, that would be just the increment at time t+1 minus the increment at time t. So if omega was going to be small in particular, if I wanted to enforce, little evolution, then there's two things that can happen. Either the increment itself, the first difference, should be small, or the increment should be about the same for both time steps. Okay, so if this increment's about the same as this difference will be near zero, even if they're both big. If both of the differences are near zero, then this will be near zero as well. Okay. So again, a question is to ask, what should we do here for omega? So here's an illustration of data marked with black X's. And this data has a kind of a clear signal. There's a general increasing trend, but then there's substantial deviations from the trend. There's these bursts of energy. In this case, they happen to all be upward. So the blue curve is a fitted curve from the model that we'll propose in a minute. And there's two sets of gray bands. The light gray band is a 95% credible interval for the mean function in cyan. And the dark gray band is a 95% pointwise credible interval for the data itself, the X's. What does the second difference look like? So the cyan curves, this is our estimate of beta, okay? And the bands are different measures of uncertainty about beta, whether they include just the signal beta or the signal plus noise, the gray band, dark gray. How is the second difference evolving? Okay, so this is the second difference of the original time series and the second difference of the path beta. So the black X's were second differences of the data. So this would have length 2 shorter than the original data to adjust for initialization. And then the cyan curve here would be second differences in the beta path. And note that we're hovering around 0 very closely and constantly for a long time. And then all of a sudden there's a burst of energy, flat again, burst of energy, flat again, etc. Go back to the original time series. How is that realized here? Well, there's a relatively smooth, in this case, linear trend, roughly, and then evolution. And then we're back, in this case, to linear trend on the same trajectory. So in terms of the modeling, what we'd like, based on this illustration, would be some time periods where there's a very extreme amount of smoothness, for example, a linear or maybe locally quadratic type pattern. But we want to be able to suddenly break that and allow for rapid changes. So the model that'll be proposed will kind of oscillate between regimes in a continuous sense, where there's little change on some scale, and then stochastic periods where there's a possibility for lots of change. When we look at the time series here, if you've done Arch and Garch modeling, this should look really familiar. This looks like volatility clustering. There's time periods or segments or small regimes that are much more volatile. Think about the vertical range of the data as a proxy for volatility. Much more volatile than others. Right? The data itself has a low level of volatility. Now it's increased for the scan, and then it snaps back, just like we might have in, say, a stochastic volatility or a Garch type model. The extreme thing that's happening, though, is that it might, in mean, it might really truly be constant or 0 in between. So we apply this to financial data, but we found a lot of uses elsewhere. This was looking at CPU usage on servers at Twitter. This time series, this is intraday data. It's fairly high frequency. We see a general diurnal pattern throughout the day, but there's lots of breaks in this time series. And we'd like to extract the signal from this time series. We want to get a picture of the overall trend, and we want to be denoting where these hard breaks are. These would mostly represent additional servers or clusters coming on and offline, reducing or increasing the load suddenly. There can still be some isolated outliers on top of that. That'll require extensions of the proposed model. We've also applied this in genomics, where we might look at copy level variation along RNA or DNA sequences. So this is an illustration. Here the axis is not time, it's a spatial location along the genome. And here's a burst of activity where the copy level deviated from some baseline standard. So how is this relevant to all of us? Well, patients that maybe have the same kind of ailment might have copy level variation in the same locations. So in this particular data set, there was a group of patients that were in a control and a patient group, and then within the patient group, all of those subjects had been diagnosed with bladder cancer. And what we were looking for was common locations along the genome where they had a coincidence of discrepancies in copy level variation from a standard baseline. Okay. And could that be an important additional risk factor for people that have yet to develop bladder cancer? So back to the trend filtering example, where we just have a intercept in a single covariate. This is maybe our simplest case. We can consider first or second differences for a penalization, but the real question is, how do we go about estimating something for omega? So I'm taking a Bayesian approach today. I'm going to think about penalizing omega as a latent parameter, and the penalty will be on it'll enforce a distribution on omega. This is a little bit different than frequentist type regularization, where we would penalize the estimated values of the functionals of the data versus a latent process. So what are the goals? Well, we'd like some shrinkage and some smoothness. For computational purposes, we'd like to utilize things in a linear sense as much as possible. In time series, that typically means that after sufficient conditioning, we're maybe left over with a component that's Gaussian so that we can loop through the data very quickly, just focusing on means and covariances. When we think about shrinkage and smoothness, no, we also now request that we have local adaptivity. Back to the earlier signals, we had extreme smoothness over some subperiods and then very little smoothness over others. And we want a model that can adapt and switch between those types of regimes automatically. So here's the proposal. We'll specify a distribution for omega, conditional on some parameters. Okay, so tau and lambda. Lambda will depend on the time index. And we'll assume that for now that the realizations of omega are independent, but they're not identically distributed. Why? Well, we'll have a global variance tau squared, but we'll have a local variance lambda sub t squared. Okay? And we'll actually just use the normal distribution. Okay. This will have a very complicated form though, unconditionally, but at each particular time point for a fixed t, we have a normal distribution. It just has a kind of separable variance function into a time invariant parameter tau squared and our local parameter lambda squared. So how would this induce shrinkage? Well, tau squared might be arbitrary but fixed. And for any given value of tau squared, we have some amount of variability that's truly controlled by lambda sub t. So if lambda sub t is near zero, or its square is near zero, the variability of this normal distribution will be near zero. So that is the mass of omega at that time will be concentrated around its mean, which is also zero. So if lambda is really close to zero, then omega will have to be close to zero. If lambda is far from zero, omega can be far from zero in either direction. So to induce adaptivity, we'd like this process lambda to evolve over time, but be data informed. And hopefully you can see just even through this simple normal distribution that we can induce very tight shrinkage about zero by using numerically very small values of lambda t, and induce negligible shrinkage by having sufficiently large values of lambda t. So this concept of global local shrinkage is not new to us. Others have earlier in the decade considered this type of decomposition. In terms of a Bayesian model, this is called global local shrinkage priors. Again, tau being the global, lambda being the local. What was the standard assumption? Well, this model was traditionally used in regression and trying to figure out in a very high dimensional regression, what are the important predictors? And the standard assumption was that thinking about lambda as a random variable, that it was IID. So what is our innovation? Our innovation is to relax that assumption and suppose that lambda follows a stochastic process, a time series type model. Okay. Let's think about this model in an even simpler context. Okay, I'm going to remove the beta term. Okay, let's just say that y itself is centered at omega. Okay. So remember, omega is the quantity, it was the increment. We have an idea that sometimes omega is near zero in this case. There's nothing special about zero. We can center it somewhere else, but zero for illustration. And then let's suppose that the variability of the signal is known. It's even 1, right? This specification is hierarchical. So, conditional on omega, y has a normal distribution with omega t as the mean. Where does omega come from? Well, it comes from its own distribution at a higher level in the hierarchy. So for a given value of tau and lambda, we have a draw of omega. How do we interpret these guys? Well, the estimator of the posterior expectation, that's the expected value of omega, given the data and maybe additional parameters, can get decomposed into a shrinkage factor, scaling the variable, the response variable y. I mostly bring up this slide. I know it's a little bit reparameterization, but it gives us a nice interpretation of minimal versus maximal shrinkage. So let's think about this parameter kappa. So what is kappa specifically with this rearrangement of terms? It's something like the reciprocal of our conditional variance. Okay, so it's 1 over 1 plus that variance term above. Oops. So when kappa is near 0, that means we do not shrink the signal at all, minimal shrinkage. When kappa approaches 1, we do very aggressive shrinkage. In this case, we shrink towards 0. So kappa is, we want to think about kappa as the percent shrinkage in this term. So it's related to lambda and tau, but it's going to be on the 0-1 scale. So what kind of distribution might be desirable for that? Well, we maybe want to just impose something at either extreme. Either we think there's an important signal at that time, in this case, and we do minimal shrinkage, or we think there's no important signal and we do maximal shrinkage. So we're either close to 0 in the kappa domain, or we're very close to 1. Okay. So this is a density function from something called the beta distribution. The beta distribution has different parameterizations, but I'm using the most common one here, and this is with 2 parameters, both set at 1/2. And we get this U shape, and this is sometimes called a horseshoe distribution. So you'll see this in the literature as the horseshoe prior. So I want, as my system evolves, I want increments omega that are either very close to 0 or very far from 0. Okay, so on the normalized scale, the shrinkage should be near 0 or near 1. So how might we go for local smoothness with local adaptivity? Well, we need to propose an evolution for that variance term. So if lambda evolves smoothly, the amount of shrinkage we have will evolve smoothly through kappa. We'd like to have desirable properties from the theoretical sense, but it's also important, especially in time series, to have computationally efficient algorithms. Typically, we have to loop through the data to do anything, and if it's complex, you're looking at multiple loops, which is not computationally efficient. So what is the proposal? It's very simple. And maybe hopefully it's familiar or will be familiar when you guys take your spring courses. And that's to consider the evolution of the conditional variance as on the log scale, first order autoregressive. Okay. So I'm taking the log of the variance term. It still has its 2 parts, that's fine. And once I've calculated that transform variable h, this is the log volatility. H is just first order autoregressive. Of course, you can do much more than this, but this is a very simple model. And it says that the next value of the log variance or volatility is closely related to where it had just been. Okay, there's a little bit of mean centering by this parameter mu, but the mean centered, subtract off mu on both sides. The mean centered value of the conditional variance is close to where it was before. This isn't a random walk. It's got a discount factor phi. So it's being driven back to the mean in general. And then there's some error distribution eta. All right, if I stopped here, there would be nothing new about this model. So the key innovation comes in doing something clever for eta. And that's to use a non-standard distribution. Okay. Eta, the innovations in the log variance recursion follow something called a 4-parameter Z distribution. Okay, this Z distribution first two parameters are maybe free. These might be hyperparameters that I'd fix, and that's what we'll do in a bit. And we need to be in a restricted subset of this distribution with the last two shape parameters at 0 and 1. It has a complex form. We won't worry about that today, but we can read more about it in the paper. I mostly bring this up is that there's different ways to characterize this so-called Z distribution. Where does this come from? Well, we didn't dream this up. It's related to thinking about that beta distribution we used for kappa, that horseshoe shape. Okay. Well, if kappa has a horseshoe shape, if our shrinkage is highly concentrated towards 0 or 1 in terms of the proportion, if we define a lambda squared as the 1 minus shrinkage over shrinkage, that has an inverse beta distribution. This is just a probability result. This is maybe one way to define the inverse beta distribution. And then if we take the log of that, this is another transformation, that is the definition of this restricted Z distribution. Well, we were thinking about log variances and those variances related to kappa through transformations like this. There's a lot of flexibility given that we have alpha and beta to also estimate. We just, for simplicity, focus on the horseshoe version of this and fix them at 1/2. So there ends up being no extra tuning parameters in the Z process. So let's put it all together. This is the whole model now for the increment process omega. So conditionally on its variance parameters, it's normal. Its local variance on the log scale follows a first order autoregression, but its innovations are very non-standard. These innovations are bouncing from something extremely low towards something in the neighborhood of 0. However, this is going to have a relatively smooth evolution, right? This is for positive values of phi. We're going to have similar, through this recursion, we're going to have similar values for the next value of h. Okay, so h itself is going to have a relatively smooth path. That means that by inverting this, lambda will have a relatively smooth path. Okay. With the Z distribution, it will be able to travel to very extreme ranges though. Okay. So remember that this will be on the log scale. It can hover towards extremely negative values. When I say extreme, it would be negative values that start to become, on the log scale, as low as your computer can recognize. So, and then on the positive side, no strict upper bound as well. One added thing, this Z distribution has a representation as a mixture of Gaussians. Okay, so I said that for computational reasons, working with the Gaussian distribution is very attractive. It just has a linear relationships between most of its parameters, and we can proceed through that. So we do utilize that as well. That's in addition to the conditional Gaussian or normal up here. All right, so I want to skip ahead and look at some illustrations of this because we've been doing most of the technical stuff. You can see how it works on some simulated examples. In the paper, we say that it's better than some existing methods. I want you to think about the signal having different amounts of wiggliness across the domain. This is what we mean by local adaptivity. The underlying signal is much smoother here than it was here, but we're able to adapt. If we did just general smoothing with one smoothing parameter, we'd never be able to achieve this. We'd either have to get a good fit with the high amount of smoothness or a good fit with more roughness. We can't balance both unless the amount of smoothness is decided locally. Computational details are fun, but the main thing I wanted to point out was that with some of the extra restrictions we made, we get a computational time that is linear in the length of the time series. Okay? And that's from the time series standpoint, that's really good. Let's go back to our time varying regression. This was the fund finance example. So here we are, we've got a response variable y that's excess returns, a bunch of fundamental factors x, and we want to see how parameters evolve. So we're going to allow those parameters to follow a random walk, but we're going to do our dynamic shrinkage model on those increments omega. Again, the goal is to have omega be either near zero or not near zero. And when it's not near zero, it'll be very data informed. It shouldn't bounce between the two very quickly. There should be longer, it should have the ability to have long stretches where this is near zero and potentially long stretches where it's far from zero. Okay, so here is our rolling regression from the beginning with the OLS lines in horizontal, black lines at zero for reference. These are our model-based fits. Okay. So we have point estimates that are coming out of our model, and they're evolving a lot like what we had before. Okay. The rolling regression gives point estimates that are fairly similar. One of the big advantages of using this Bayesian approach now is that we also have envelopes about these curves. We can also conduct inference and say, for what time periods was this coefficient significantly different from zero? Well, it looked like the intercept that there were a couple time periods where it was significantly different than zero. We had negative alpha in both these periods. How about the risk or the market return? It was always significantly different from zero at all time periods. Of course, zero was down here, but we needed to verify that by measuring the uncertainty of our curves. How about these other factors? Well, the capital asset pricing model says all you need to do is regress on the market. All you care about is that scalar beta. Three-factor model says you need small minus big, high minus low. When we look at this in a time varying fashion, now we question that. Is that true that we universally need that? Or are there just certain time periods where that has a big impact and you have a trading advantage or an explanatory advantage? Okay, so there's long stretches where we get significance that's different than zero. And depending on the time frame we look at, that's more or less important. Well, it turned out in the manufacturing example, there was tons of periods where each one of these factors was important. And in fact, when it was important, it maybe even had a different sign. Okay, this was the momentum factor. It had a positive sign through the 2008 financial crisis, then switched to negative. I didn't talk about it, but I also have a second stochastic volatility in the model, and that's for the measurement error. Okay, so the returns themselves might have stochastic volatility, not just the time varying trends in the coefficients. How about the healthcare industry? And you can do this for individual stocks as well, and develop kind of adaptive trading strategies. Here's the fitted model for healthcare industry. Here we didn't see a single time over these 20 years where, and this went through 2017, where there was a non-zero alpha. How about the market? Well, there was a dip early on, but it still was always significantly different from zero. When we interpret these, remember, it's not the marginal contribution. All these parameters are in the model at the same time. So you have to say, is it significant conditional on what else was estimated in the model? But having accounted for the market excess return, there's long stretches where small firms, the difference between small firms and big firms was important. Similarly over here with book to market ratios. The timing of this differed, and we think that this is important. We haven't gotten around to doing an empirical study yet, but the timing when different betas is important seems to have very different patterns based on industry. So keep track of these red bars for the different factors below, and note that they're different times when they're important for healthcare versus manufacturing. And this could be utilized to come up with trading strategies that cycle through different industries. Okay? So And it's not that you know what the returns are, it's just that you maybe have more confidence in the predictors for excess returns in those time periods. I think I want to skip ahead quite a bit and just preview a couple extensions. So I'll just point at a couple graphs as I skip ahead quickly. Here was the trend filter applied to that CPU data. You get really quick breaks. This is on the second difference. We see that the fitted model is having that volatility type clustering. So these bursts in the second difference correspond to these rapid changes or discontinuities in the curvature or second derivative. I mentioned before the measurement error adds stochastic volatility. That means that we allow the variability of the noise about the trend to change. So this is, the trend itself is changing, and it changed through here, but actually the black dots were more variable about the trend as well. Okay, so we believe that both can be evolving, variance and mean can be evolving at the same time. And that's easier to see after we've removed the trend effect on the second difference scale. The right part was much more volatile than the left. This was on the genomic data, and these indicators, if these held up across being important locations on the genome that were special to or distinct for control versus patient groups, these could be used as risk factors for early screening for different types of cancer. A couple extensions. I was doing this for scalar regressions, but we can have a vector. Things get more complicated, but I'm pretty into vector modeling and higher dimensional modeling in general. How about change point detection? And this is what I'll preview for a few minutes now. Change point detections of a little bit different flavor. Okay, the shrinkage model so far allowed local adaptivity, but it did it in a way that said, you're basically constant on either the first difference or second difference scale, and then you weren't for a little while. A change point model would be a hard break at a particular time. Okay, I'd say you maybe piecewise linear, for example. So the very basic extension is to switch from just a first order stochastic volatility model to what's called a threshold stochastic volatility model. So we have some indicator that's tracking how big our increment was, in this case in the squared sense. Okay, so there's even additional latent variable. And what this does is it says that if we have a really big jump, we want to drop the conditional variance down so that that jump becomes isolated. We want lambda, when it gets big, we want it to be big instantly, but then come right back down. So I'm skipping ahead through a few more examples. I want to get to this part. This is with a different co-author. This is one of my current students, Peter Wu. And he's worked on, and he just got this on arXiv this week, adaptive Bayesian change point analysis for local anomaly detection. I'll just spend maybe 1 or 2 minutes on this, but I did want to thank you guys. It was very motivating having this talk and getting this paper online this week. So I appreciate that. Our algorithms for change point analysis using this dynamic shrinkage idea is called ABCO. It's very similar to before. It's going to have a time varying, so this will be posed in the trend filter sense, time varying signal, measurement error or local noise. This local noise can have non-constant variance. And now we have an additive outlier. Okay. So we're going to have an additive outlier, zeta, and this should be an isolated outlier. The outliers are kind of a priori assumed to occur at independent locations. And when we do the trend filter on beta, we want to use that idea from before, that I just mentioned a few slides back, where we utilize not the stochastic volatility model, but a threshold stochastic volatility model for beta. So again, this is what we had before. In terms of the outlier term, we use a heavy-tailed distribution, more heavy-tailed than the horseshoe. And this just says if the term's really, really big, We think that's important, but we're attributing it to the outlier. We're not attributing it to the signal. We're not attributing it to the noise. So we have an unpenalized term if there's a very extreme observation Y, and we filter that towards this additive outlier. We can use that for outlier scoring. So it's the amount of variability that gets attributed to the variance of zeta versus the variance of the local noise epsilon. So it's just the proportion of variability. Here's where we have our threshold model. And then I want to just go to the plots because they're fun. So this is a synthetic example, but we're looking at a single time series, and we've got very clear volatility clustering, non-constant variance. The signal itself in this case was piecewise constant. Okay? So our model allows for a general trend. In this case, the true trend was piecewise constant. So it knew to numerically shrink that trend very close to zero. So it's the increment that's numerically very close to zero. Here the mean's a little different, but it's very flat. The increment as we move from left to right in this piece segment is very flat too. But we now have very isolated, very sharp breaks. Okay? So this is very extreme amount of smoothness and a single time point where there's a hard break. And these are the change points. We threw in a couple outliers in this illustration. Typical change point methods will chase these outliers. They really struggle with non-constant variance and they chase outliers. They think they're important breaks. This is a pretty substantial deviation from the local variability. But by explicitly modeling those outliers, even though they might visually appear close, given the local variance at that instant, this one was scored relatively high on the outlier scores. We use shading to color all the points by their outlier score. In terms of signifying some of a change point, we have marginal change point probabilities that come out of our model. Here's another example where we can show that if you don't do the anomaly detection, you think there's more breaks. So if I turn the anomaly detection term off, if I don't include it, I include a lot of breaks around anomalies. I think the mean itself changed, not just that that was an unusual observation. Can I ignore stochastic volatility? Well, if there's none present, I'm okay. But if there is stochastic volatility present and I ignore it, I'm in big trouble. Okay, so this model ignored stochastic volatility, but the data itself had it. So this data had more volatility in this regime. It was volatility in the error, though. It wasn't in the signal. The true signal was closer to what we had over here. So you can ignore outliers and ignore constant volatility at your peril. Even if they're not present, you could try out ABCO. It will shrink things towards zero if they're not needed. So in this time series, there was 5 true outliers. There's 2 of them in a row down here, and 1 true break. And we did quite well on that, but we'll do more extensive simulation studies to validate that. You can have meetup models. This is more of a structural break type model. Piecewise linear models, any parametric type shape you can have. And then we did apply this to a few different real world examples. So here's one where it seemed some alternative change point methods maybe chased outliers. They put in a lot of small increments for this relatively smooth trend. ABCO's a little different style. It allows for an evolution in the mean, but it separates that from slow varying trends versus hard breaks. Okay. This is something you can adapt to. This probably isn't. So I think with that, I'm done. So thank you guys very much. I hope I'm close to on time.
Yeah, you did great, David. That's very interesting topic. Does anybody have any questions? If not, I have a couple questions.
Yeah, go for it. And people, if they're shy, you can always email me or.
So one of the things, and like you alluded to using some real data, and anytime I see anything involving time series, the first thing that pops into my head is, how does it do out of sample? So did you have an opportunity to look at, I use this model, and then I, found a way to sort of look how it performed out of sample in a way that might be useful to a trader?
I would say probably not useful for a trader yet. This isn't necessarily a forecast model. We do, sorry, I'm trying to go back to some simulations that I skipped. What we can do for trend filtering, for example, is randomly remove data points and then infer what they would be. So we can pull out, you might do this in chunks, so that's a little bit harder problem, and pull out blocks. And then conditional on the data you did observe, you've got missing values at this point, and can you impute what they would be? And so these types of simulation studies say, well, we get much lower root mean squared error when we use our full model with all the bells and whistles. What you're most interested in, probably as a trader, is trying to say something about hold-up samples that are only on the right. I think what we can offer is a better quantification of uncertainty at your forecast origin, but I'm not really willing to say that we can give better point estimates consistently than other approaches. So what does that mean? Well, if I want to predict what's going to happen tomorrow, what I'm trying to say is I probably have no better ability to pinpoint the precise value, but I think that I can get a more accurate interval than other methods on average. So, in repeated forecast experiments, I think that this adaptive type model better centers the mean for the next period based on this local smoothness assumption, and has more adaptive widths for the prediction interval for that mean, the light gray, and the prediction interval for the observation, the dark gray.
So would I be correct to translate that to saying that if you give a 95% say forecast cone, even though you're not forecasting per se, that your cone is more true to that than say another forecast, maybe a more simplified forecasting method?
Yes.
Where where, for example, it's not a question of whether what really happens falls inside or outside of the cone. What the matter is that what falls outside of the cone should only happen 1/20th of the time.
Yeah, we believe that we have better frequentist coverage in that sense. So even though it's a Bayesian model, because of our local adaptivity, that if we run that experiment 100 days in a row, and we're focused on 95% coverage intervals, then I'm claiming, yeah, I will be closer to inclusion at the 95% level than most traditional methods, and actually most state-of-the-art methods. That's a claim. The proof is, can you do that in the market? It's more interesting if you do it in the market if it's tied to, an asset that's actually traded. So you might be looking at assets that are related to the volatility of the returns themselves instead of the price itself. So don't use this for predicting stock prices, but maybe it can tell you something about, in particular, is there some momentum, and how consistent is it based on the smoothness of the path, and where does volatility look like it's going, given that you've accounted for a time varying evolution and trend.
So I have on record you're disclaiming buying stocks on margin using this model. Is it?
Yes, that's right.
Okay. Any other questions? I have more, but I want to give the audience opportunity to ask other questions they might have.
I guess I just have a quick question. I was just curious about the data processing. You said you used weekly data. What was the reason for that?
When we first implemented this model, everything was in R, and R is not particularly efficient at looping. So once we got sample sizes that were in the tens of thousands, it became very painful to fit the model for simulation type studies.
Oh, I see.
So
it wasn't for a seasonality?
No, it wasn't. It was a kind of a time series length thing. But yeah, it does bring up a good point. We kind of wanted smoothness, in this case, across the weeks. You can have pretty regular breaks because of weekends and holidays. So that might be a place where you maybe want to include the change point type term or the outlier type term into your trend filtering if you switch to daily data. I'd love to try this on intraday data at some point too. I imagine that I guess maybe like 5-minute increment type stuff. But there'd be new features of that data that would demand model extensions. I don't know that it would be adequate for intraday data as is.
Do you feel and then that there's a need to maybe translate some of the work out of R and into some other type of software?
Yeah, I'm looking for interested students that would like to at least code a couple of those loops in C. That's one of our traditions, is to mostly prototype in R, and then there's an interface with C that's not too challenging, and you can basically anytime you loop over T, the time index, you might like that loop to be in C++.
So John, are you going to pitch Julia now, or?
I thought about it, but I'll let him find it on his own.
No, I'm familiar with it. There's we're doing a couple kind of, for this, we're doing a couple exotic sampling things. So I guess we'd also need help coming up with ways to sample the Z distribution and things like that. So I don't think Julia has all those probability models in there quite yet, but it can. So
Grad student project. Right.
yeah, it is good. So are you guys fans of Julia? I mean, I've known about.
Oh,
it
I
for
think
several
John. I
years,
think
but-
John is. I'm still withdrawing from MATLAB. So.
Okay. Well, yeah, it's about a third of my students are in applied mathematics, and they all still use MATLAB, and most of my others use Python or R. So yeah, Julia, I guess I need to learn more about how it works in a Bayesian setting. So certainly just standard loops, it can do that real-time compile after the first one, but with the random number sampling, I guess I'm just not familiar with how it works.
I don't have any. I mean, because we're 35 past the hour. I'm gonna withhold my additional questions.
That's fair.
But I would encourage any other participant, if they have a question that they're burning to get out, this is your chance. And not hearing anything, I'll just say, David, thank you again for taking your time here on a Friday night to talk about sort of an esoteric topic. I know that actually this is actually time series is always a very fascinating topic, at least for me, because there's so much. It's kind of like a wild animal, and there's so many things that you have to try to pin it down. It's really difficult. So I really appreciate some of the efforts that you're doing here.
Thanks a lot. It was a pleasure, and thank you all for attending.
Thank you. Actually, I may have a question, but would you mind I send you an email?
That is no problem. That's perfect.
So Chang, if you need his email, I can get it for you.
Okay.
Oh, okay. Yeah. Thank you. Have a great night.
You too.
All right. Thank you again so much. And then if you get a chance, David, to send me slides, that'd be great.
I will do. Thanks a lot.
All right.
Take care, Gary. I hope
All
to
right.
meet you in person someday.
Yep.
All right.
It'll happen.
Yeah.
All right.